9. Yeah, so it's much more heavier than me, right? So, yeah, I'm nothing compared to the sun. Anyways, so he said such dark stars are much, much heavier than the sun, and they have the escape velocity. So here the escape velocity means the minimal velocity needed to escape a planet or some kind of object. Okay? So that means we have to go against the gravity, and that's called escape velocity. And such escape velocity is greater than the speed of light. And c is the popular notation for the speed of light. And he sent a letter in the year 1783. And in that letter, he acknowledged that his ideas were not practical at that time, but it will be helpful to future generations, so that the future generations, like this person, can use it. Okay, so I guess everyone can recognize who this person is because he is, I believe, one of the most smartest people in the world history. So Albert Einstein. So he lived from 1879 through 1955. And the reason he is popular was because of the discovery or the invent of the special relativity in 1905. So there was a kind of funny story about special relativity. That is, he was working at a patent office at that time, and one thing that he was doing was he was reviewing all the patents that was submitted. Okay, and at that time, so he was working in Switzerland, and at that time, the time between different cities were different. So, for example, like the time at Bern, which is like one of the Swiss cities, is like 12 o'clock. Then the nearby city has different time. So that kind of caused a problem because technically, like where I stand right now, like suppose I'm standing at 9 o'clock, then if I move just a tiny bit here, the time has to be different. It's what's supposed to be. Well, of course, that's not actually true in these days, right? But at that time, it was different. So there was a machine that was invented to convert between each time differences of each city. And he was reviewing such machines so that he can give out the patents. And then he came out this theory of relativity. And there are two conclusions. One of the conclusions is the laws of physics are the same for non-accelerating objects. And then there's this second conclusion, which will be mentioned in just a few minutes. And then there's this general relativity. And this one came in 1916. So the special relativity simply means the gravitational effect is negligible. And also, something called space-time, which will be mentioned in the next slide, is flat. But the general relativity assumes that the gravitational effect is possible and in fact exists. So this one is about rotations and gravitations. So this one is the more general case. And the term about the special relativity is because the special does not mean like peculiar. Special means special case. So special relativity is the special case of the general relativity. And now, Einstein came up with the field equations that looks like this. Okay, so it looks complicated, yes. And what's meaning of each of these expressions is this one. So the first term, R and then subscript, and that's the Greek letter mu. And then the second letter is the Greek letter nu, not the V. And that simply means Ricci curvature tensor. Now, the term tensor, so there are some various ways to define a tensor, but one easy way is the generalization of vectors. Now, maybe you have not heard the word vector, but vector simply means the arrows. Well, of course, it has mathematical meaning. Okay? So the tensor is a construction that eats up a bunch of vectors and then spits out a scalar or the number. That's what tensor is. And such rich curvature tensor is about matter content of the universe. Like that's the meaning of the R sub mu and nu. And then the R, okay, so the R, remember, appeared right here. So this R stands for the scalar curvature. Now the term curvature means it's the measurement of how the curve deviates from a straight line or how surface deviates from just plane. Okay, so for example, this is a curve, and this, like how much it is curved compared to this straight line is the curvature. And of course, if you want to extend our concept to 3 dimensions case, then we can talk about the surface and the planes. So that's what this R stands for. And then the G subscript mu and nu. So that is the thing in between 1/2 and R. So that stands for the metric tensor, and what it represents is the gravitational potential. So let me write this on this board. So there is this Newton's law of gravity that looks like this. So that's the Newton's law of gravity. And here m1 and m2 are the 2 masses of 2 objects. And then r is the distance in between 2 objects. And then this g is the Newton's gravitational constant, which is a fixed number. And it has some kind of weird unit. So the actual number is 6.67 times 10 to the negative 11, so it's really small. And then the unit is kind of weird. It's meter cube over kilogram times second squared. So normally we represent the units in metric system, not our system, right? So I'm kind of sticking to the meters, kilograms, and seconds. But so that's the meaning of the G. And so that's the law of Newton's gravitational potential, and basically that has something to do with that G sub mu b, or mu nu, okay? And then the thing on the other side, so I guess everyone knows what this symbol is, because that's really popular, even for like basic math people. So that's a pi, right? Yeah. And then G is the same G as that, 6.67 times 10 to the whatever. And then c to the 4th. Okay, so c was the speed of light, remember? And then there's this t subscript mu nu. And that t subscript mu nu stands for the stress energy tensor. And what that means is the density and flux. So flux means kind of the strength of flow of energy. So it kind of combines all of the universes, and that's why it's called field equations. Okay? And actually, when Einstein came up with this field equation, there was this extra term after 1/2 G mu nu R, and that is this one. Now, this stands for the Greek letter lambda, the capital letter, and then G sub mu nu is the same thing as before, the tensor. And this one is called the cosmological constant. And when Einstein invented this general relativity, he developed based upon the fact that the universe is not expanding. But it's actually false. The astronomer Hubble, I think maybe you might have heard his name. There's this Hubble telescope in the universe. The Hubble proved that the universe is indeed expanding. So this lambda is actually false. So Einstein later said, inserting this lambda and then G sub mu nu was his biggest mistake of his lifetime. So he deleted this lambda term. later on. But, so that's why this is the Einstein's field equations. And then we have looked at what each term stands for. Okay, and now, there's this interesting thing about this relativity, and that's called space-time. So, this looks like a combination of two words, space and time, and it is indeed the case. So, space, which is kind of like in this room, for example, is a three-dimensional space, right? Because we have this line, and then a plane, and then this height. So it's three-dimensional. And now, time is one-dimensional because time only flows from past to present, and then future. So it's one-dimensional. If you combine these two concepts, we get space-time. So space-time is actually 3 plus 1, so that's kind of easy math, 4-dimensional concept. And we cannot see this space-time. So people say, well, in the room there's a clock, so it's a space-time. Well, no. Like time, we cannot see the time in like as a dimension. So this space-time only exists in the imagination. But there is this concept. And the reason that this space-time is important was because in the special relativity, so one of the conclusions was the laws of physics are the same for non-moving observers. And the second conclusion is this. The speed of light in vacuum is the same no matter how fast a person moves. So think of the c. So c is the speed of light, remember? And speed has something to do with the time. And an observer exists in the real world, so he or she lives in the three-dimensional nature, like maybe in the room or maybe like on some land or whatever. So this special relativity shows space and time are not separate. They are related. And in particular, like I said before, the space-time is flat for the special relativity because we have to ignore all of the gravitational effect for the special case. Now, for the general relativity, so the biggest conclusion is heavy objects cause distortion and curve of space-time. So basically, heavy objects has strong gravity and it will cause distortion of the space-time. Okay, and an easy example is, so suppose I have a paper here, and then I place an object like here. Then the paper is bended, it's curved. So think of this remote control as like heavy objects with the strong gravity, and this is a space-time. Then if you place it above this paper, the paper will be bended. So that's the example of this general relativity. So that's the conclusion of the general relativity. And then, okay, so now, going back to the history. So his name is Karl Schwarzschild, and he lived pretty much at the same time as Einstein. And the importance of this person, this scientist, is he first came up with the exact solution of the Einstein's equation. So earlier we have looked at Einstein's field equations, which involved all bunch of tensors. And that's just an equation, and any equation has answer or solutions. I guess for those who took college algebra, you'll know that, right? So he gave first exact solution in metric form to those equations, and we'll look at the solution forms in a minute. And another important thing that he came up with is this number, Schwarzschild radius. So in a few slides, we will look at this number yet again. And R subscript S, so S came from his initial, Schwarzschild, is equal to 2g, the Newton's gravitational constant, 6.67 times 10 to the negative 11. And then m is the mass of an object divided by c squared, that is speed of light squared. So he came up with this number, and he claimed in his work that any star with a radius smaller than that must appear completely black. So here comes the word black hole. So the John Mitchell, the guy who appeared first, he first designed the idea of the black hole, but the term black hole was not invented until this person. So he came up with the word black hole, and he gave the exact same solution to the Einstein's equations. So, speaking of the solutions to the field equations, let's look at something called Schwarzschild metric. So, think of metric as something to measure the distance. And for that, we need special coordinates. Now, mostly in math, we use just number line or xy plane. So we have x comma y in particular for xy plane. Now, maybe you have seen x-axis, y-axis, and z-axis as well. So that's three-dimensional. And now, remember, space-time is a four-dimensional case. So insert one more variable. So this is a ordered four-tuple. And we have t stands for time, and then r, theta, and the last letter is rho in Greek. And that r, theta, and rho are called spherical coordinates in multivariable calculus. But the solution looks like this. Okay, so this has nothing to do with college algebra, first of all. So I'm sorry for causing massive confusion. But so here, the letter d's. So there are a bunch of d's, ds squared, and then dt, and then dr. So the letter d stands for differential. So for those who have taken calculus before, you might have seen the letter d before. And here, oops, I forgot to insert one more line. Okay, there we go. So there are extra d's as well. So you can see here, you can see that t, and then r, and then theta, and rho here. So once you solve this equation, or in a metric form, you get the exact solution of the field equations. But the actual solution has, there we go. So the actual solution is really complicated, so I'm not going to write that down. And this Schwarzschild metric is based upon the fact that the black holes are not rotating, so like this. But some black holes are rotating, and for the rotating black holes, we need something else called Kerr metric, K-E-R-R. And the Kerr metric is a little bit more complicated and uglier than this. So I can write that down. I cannot even memorize it because it's really complicated, but I can show you how it looks like, and it's fairly ugly. So the good thing is the left-hand side is the same, ds squared. How nice is that? And now the right-hand side is a little bit different. So first we have negative 1 minus 2mr all over rho squared, and then dt squared, so here comes the t again, and then minus 4mar sine squared theta all over, yeah, I know, this is kind of, I just want to show you how it's ugly compared to this. Yeah, like that's all. Like I'm not trying to like educate you like anything about this, so no worries. Even I was confused like when I first saw it. And then, yeah, so bear with me. Like I'm more than halfway done. I'm more than halfway done. I'm more than halfway done. Yeah. I just want to write it down. Like that's all. Yeah. I'm not expecting anyone to understand this, including myself. So, yeah. Okay, so that's the exact form. Okay, so what's the biggest difference? It's much more lengthier than this. Oh wow, okay, so surprising, that's the absolute discovery. It's a lot longer. Okay.
How long do you know how long it took them to like come up with that?
with that equation, it's him.
Like, do you know how long it took them? No.
Long time. Super long time, I believe. Yeah. Yeah, so I guess one obvious fact is I would not have come up with this thing because, as I keep telling to my students in my classes, I'm kind of stupid. So, yeah, see? Yeah, I tell that always, and no one believes it, but I don't know. Anyways, okay, so that's the current metric, and this one works for the rotating black holes. But this one is for the non-rotating black holes, like stationary black holes. Okay? Let's just go to the next slide because no one wants to see that anymore. Okay, there we go. Okay, so now, I guess the better thing that we are all interested in is how is the black hole formed. So, first let's start with the heavy star. And inside any star there is a core. In fact, our Earth has a core inside, like way inside. There are actually 2 layers of cores. But any star has such cores. And now, this core grows larger as the time goes. And as the core grows larger, the hydrogen is converted into Fe, which means iron, for those who have taken chemistry before. So hydrogen is converted into ions. And then the star just keeps growing, and at some point it will cause explosions. And that's called, in a fancy name, supernova. And I guess maybe you have heard about that before because that's kind of famous term. So supernova means big explosions. So when the star collapses due to the supernova, the core actually does not disappear. Rather, it keeps shrinking. Okay? And now, when it keeps shrinking, now why does it shrink? Because any star has big gravity. And it causes the core to keep shrink. Like imagine there's a core here and then you are pulling the core down. Then it will shrink. And there's a reason for this strong gravity. And maybe you have seen this formula before. That's the rho symbol. And then is equal to m over v. And this one is the density formula. So in words, this formula means density is equal to mass over volume. So V stands for the word volume, and then M is the mass, the kilogram type thing. And now, here, so now let's go to some college algebra / calculus type math. So, maybe you have seen the graph of 1 over x. Okay? And the graph looks like this. These 2 curves. Okay? So, think of V as x. So instead of x, we have v. And then m is like a fixed number. So that means it will maintain these 2 graphs. Now, any volume is positive, it can't be negative. So when the volume becomes very small because the core is shrinking, then what happens is, so now this is a calculus, so this is a limit. So your volume goes to the 0 from the positive direction. So that means your volume goes into here. Because that's the 0 part for V. And your volume goes to the 0, so that means it's going this way. So on the graph, it's going up. So what happens to this m over v, or this density itself? It's going to the infinity direction. So that's why we have strong and strong gravities, because the density is really high when the volume gets very small. So now, a professor whose name was Dr. Maeda, so he's Japanese, from a university in Japan, he showed in his work that such shrink can occur up to the diameter of 10 to the negative 33 centimeter. Okay, so again, what that means is, I didn't mean that. I didn't mean that. Oh, somehow it got turned off. There we go. Yeah. Yeah, so I guess this computer knows what you all want to see, right? Exactly. Yeah. It's understandable, right? Yeah, it's much better than like all of this like crappy stuff, I guess, right? Anyways, so 10 to the negative 33 centimeters. So that's really small, right? Because what does that mean? It's 1 over 10 to the 33, right? So it's 1 over 33 zeros. So it's like 0.33 zeros and 1, right? Yeah. So it's very small, okay? And it's unknown what happens after that. That's how he claimed in his paper. So now let's look at some components of the black holes. So the first thing is the gravitational singularity. And an easy example of that is 1 over 0, the fraction. Okay, math people, what is 1 over 0? Undefined, right? Yeah, if you say 0, then you are close, but yeah. Yeah. Okay, so review, I guess. Okay. Yeah. 1 over 0 is undefined. Yeah, it's bad. Okay, it's bad. So basically, when the denominator is equal to 0, you are falling into the black hole. Okay, so this gravitational singularity means a location where things measure the gravitational pull cease to depend on coordinate system. So that means gravity says, I don't care what happens around me. I will go my way. So it's causing very strong gravity. And that's why I said deep hole. So that's the actual black hole part, like a bullseye. And then another component is the event horizon. So the event horizon is the region or the boundary between the outside region and the black hole itself. So basically, like here's a paper, and in the middle there's a black hole, and that is the event horizon. And outside of this boundary, the black hole has no effect. And this event horizon is called the points of no return because when you enter this paper, the black hole territory, you cannot escape and you'll be absorbed into the black holes. So that's why it's called points of no return. And this is not the component of the black hole, but it's something that's experienced around the black hole, that's gravitational lensing. So gravitational lensing means it's the phenomenon that the light is bent when it travels nearby gravitational field because of the strong gravity. So remember, I put this remote control earlier here, and it caused the bend of the nearby space. And suppose your light travels to the Earth, but it somehow passes this paper region, then on this region here, near the black hole, it will cause the deviation or the curve of the path because the nearby space is bent. So that's why it's called gravitational lensing, and it shows nearby space is bent. And the real component of the black hole, like another one, is this radius, Schwarzschild radius. So we have seen this value before, and this is the radius of the event horizon. So basically, this is not the radius because it's a rectangle, but suppose this is a round object, and the radius of that is the event horizon, or the Schwarzschild radius. And now, this threshold radius makes sense not only for the black holes, but also many other objects. So as long as your object has a mass, you can plug in the mass here, and then the fixed value g from earlier, and then speed of light at the bottom, and you can find the threshold radius. And what that means is, it's the radius of the range where the gravity of that heavy object affects. So in particular for the sun, so the mass of the sun is, I think I wrote that down earlier. So the mass of the sun was 2 times 10 to the 30 kilogram, yes. So that means 2 and then 30 zeros in the back. So plug that into m, and then g is 6.67 times 10 to the negative 11. And then c is 300,000. So 3 times 10 to the 5th. That's the meters per second. So again, we are sticking to the metric system, not feet per second or miles per second. So when you plug in all of that, you will get the threshold radius of the sun is about 3280 feet, which is huge. Okay, so that is another component of the black hole. And now, so let's go to the time component part. Okay, so can time also be bent? So this is from a thought experiment. So that means this experiment is done by Einstein in his brain. I would never have done that, but whatever. He was smart. He was smart. So basically, he imagined 2 identical clocks, one placed at the rotating disk right here, and then another is at the center. Okay? And now, suppose there is a person at the center of this disk. So somehow he or she is standing at the center of the disk. Now, what this person sees is that the clock at the center has no velocity. That does not mean the clock is not moving. It is moving, but it's not like moving like this. Because the position of the clock and the observer is the same. So the clock is not moving, it is ticking, but it's not moving. But the one at the edge is rotating. And according to the general relativity, the more acceleration you have, the slower time moves. So the clock at the edge goes slower than the one at the center. And that's what this picture shows. And in any gravitational field, in fact, depending on where you are, where the clock is, the time will go slow or fast. Okay? So let's look at what this even means. So time goes slowly. So remember, space and time are not separate according to the relativity. They are related, interwoven. So time goes slowly means the speed of light, which somehow relates to the time, is slower by the same amount as the speed of falling due to gravity. And we'll see this phenomenon once again in a minute. And suppose there's an object that falls at the speed of light, and it emits the light in the opposite direction. So the pictorial example is this. So here's an object, and it's falling this way. But in the opposite direction, it's emitting the light. So that means you will carry the speed of light c. Then, what happens is, an observer at a far distance, so maybe here's an observer here, at a far distance, sees the non-moving light, stationary light. So that means it does not fade or brighten. Why? Because if these two speeds are the same, and since both are moving in the opposite directions, they will cancel. So it's like C and negative C. So that means the light does not fade or brighten. So, and now here is another thought experiment, and this one is also done by Einstein in the year 1896. And remember, he was born in 1879. So this one was done when he was 16 years old. I don't know what I was doing in 16 years old, but I was not doing any thought experiment like that for it. So, suppose that a person, A, is falling towards a black hole. And for simplicity, we can assume that this person emits the light to the opposite direction like this. Then, suppose there's another person B at a far distance. And, so for example here, this person thinks that the person is not moving or is extremely slowed down. Because remember, these two speeds cancel. So this person A seemed to not reach the event horizon, but was the reality. He or she is actually sucked into the black hole really fastly. So this shows that the closer a person is to a black hole, or becomes closer to a black hole, then the time goes slow as well. And here is this picture. And this picture is kind of confusing. So there's this R sub s, so that's the Schwarzschild radius. So here's the start of the black hole. And a person is falling this way. So that means this is the actual location of the singularity, the deep hole. And this is the line of infinity. And suppose you are standing right here at the bottom of the line. And it says my personal measure of time is straight up, so that means the time passes like this way. Okay? And this person is not moving, but the time is passing like this. So it seems like the person is moving, but actually the time is moving. And now this person witnesses another person that's falling like this. Okay? Then, since this is the start of the black hole, this person gets sucked into the black hole in a short period of time, but because the time go fairly slow starting at this point, what it says is the distance observer will see the body freeze near the event horizon because, like I said, look at the stationary light here. So it seems like the person is momentarily stopped. The light does not fade or brighten, remember. But from her point of view, the time seems to pass very slow there. So the person is sucked into the black hole like this, and the person is standing right here, another person, and this is the time direction. So basically the person at this point, at the bottom of the line, cannot see the other person right here. So that person has to wait a little bit longer, so that means the time is passing, and then until this point, so that this person realizes that another person is falling. So it's not just the straight perceive of the falling because of the delay of time. Now, how to detect black holes? So, even lights cannot escape the black holes because it has such a strong gravity. So how we detect black holes? One way is to examine the X-rays and jets that came out from the black holes. So basically, the nearby stars, when it enters the event horizon or goes fairly close to the event horizon, it emits gas and dust. And those emitted gas and dust form a rapidly spinning disk around the black hole, and that's called accretion disk. Maybe you have not heard its name, but it's spelled like this, accretion disk. So this one is the fast-moving disk around the black hole. And then those gas and dust lose kinetic energy, so that means the motion. Kinetic energy means motion. So they lose all the motions and speeds because of the friction against each other. And the gravitational tide, so basically the gravities near the black hole tear those gas and dust apart, and then it heats them to very high temperatures. Okay? And when it does that, X-rays are emitted. And when X-rays are emitted, very bright light comes out around the black holes. But as soon as the light came out from the black hole or this after heating process, it's immediately absorbed because of the strong gravity. So that's why we cannot see the black holes. So somehow it was like really bright for like maybe like 1 second or so, and then you cannot see it because it's absorbed to the black hole once again, even the light. But NASA, which is the group of like the smartest of smartest, right? So they came up with the first actual picture of the black holes. And it looks like this. So this black hole is in the galaxy called M87. That's the name of the galaxy, M87. And this M87 is 53 million light years away from the Earth. So now, the term light years, what does that mean? So the speed of light is something per second, and now there are 60 minutes in a minute, or 60 seconds in a minute, and then 60 minutes in an hour, and then 24 hours in a day, 365 days in a year. So multiply all of that times 53 million. That's the distance from the Earth. So it takes for light to travel 53 million years to get to this M87. So it's really long, right? It's unimaginable. Okay? So basically NASA took the pictures of this galaxy, several pictures, and then they have synchronized the images and compiling the data. They were able to come up with this picture. So they just didn't like take the picture of this like by looking at the M87. Okay, here's the black hole. Take a picture. Boom. No, they didn't do that. They took various pictures and then they knew beforehand that the black hole exists in this galaxy. And then after compiling several images, they came up with this picture. And this black hole is very massive. It's about hundreds to billions of solar masses. So it's very heavy. So now, I guess I'm running out of time, so I have to go quick. That's kind of my one problem in all my classes. I always fall behind. So now, let's go to the other holes. So there was a black hole, but then maybe you have heard these two other holes, wormhole and white hole. So black and white are opposites, obviously. So black hole is the entrance only because we can always be sucked into the black hole, but we cannot escape. White hole is the exit only. So one can only exit through this black hole here. And then wormhole is basically the bridge in between these two holes. So the thing is, the wormhole and white hole are hypothetical regions. We don't know whether they actually exist. But although we know for sure that the black holes exist. So, is the time travel possible? Because once we enter the black hole at the present moment, we can exit through the white hole. Again, if we assume that it actually exists. And now, where are you basically? Are you still at the present? Or are you in the future? Now here I put past, although the time only goes from past to future because we don't know what's going to happen inside the wormhole. The time might be reversed and flows in a different direction, like opposite direction. From future to present to past. Who knows? Okay. So the legitimate questions that has yet to be answered is, do they actually exist? White holes and wormholes. Because no one has proved that such things exist. Now, number 2. What happens when we enter the black hole? So I guess one obvious answer is like, we die. Yeah, of course. Yeah, that's a legitimate assumption. But still, suppose we can enter the black hole. And is that even possible? And now, question number 3. can we send the spaceships to the black holes and make them enter the black hole? So I know there's like a spaceship that just keeps traveling past like solar system, but can we send a spaceship that's like 53 million miles, or like not miles, like light years away? It takes for light to travel 53 million years. Can we send spaceship? Well, at the moment, no, but maybe the technology is developed in the future and maybe we can. I don't know. And the closest black hole, actually, so this one is kind of far from the Earth. The closest black hole is labeled as V616, and this one is fairly close, 3,300 light years away from the Earth. So it takes for light to travel 3,300 years only. It's like a neighborhood. Really, like in the universe, seriously, like this is like a neighborhood. It's like just right next door. Yes, it's like really close. Okay, like this is nothing. So maybe we can send a spaceship to this black hole and make it enter, but still, this spaceship has to travel for nearly 5,000 years, I guess. Because for the light, it takes 3,300 years. So maybe for the physical spaceship, maybe it needs more than that, maybe 5,000 years. Yeah, so that's kind of a better question, I guess. So now, the next question is, when we exit from the black holes, where are we? Are we at the present? Like maybe a few minutes afterwards? Or maybe are we at the future, like maybe 100 years after? Or are we at the past moment, like 50 years before? We don't know. And another question is, can two black holes collide? Which means, can a black hole be sucked into another black hole? So this is kind of like contradictory, because black holes have strong gravity, and each one is pulling the black holes each other like this. So what will happen? We don't know. And then another question, will the time go slow at the white hole? Because the time goes slower around the black hole. So for the white hole, since it's the opposite, will the time go faster? Or will the time will still go slow? So we don't know. Okay, so that's all my presentations. And does anyone have any questions? We are like running out of time, I guess.
Okay, so if you went through the black hole, how would you know what time it was when you got through?
Okay, so let's go back to this picture here. Okay, so here, inside the black hole, you only have one direction of moving. That's from outside to inside. So some scientists say the space is like a time inside the black hole, which means the time is just one dimensional, right? Because the time goes from past to future. It's just one dimension. But in the black hole, the space is one dimensional. So space is like a time. So we cannot measure the time around the black hole. But suppose we can just measure it like maybe from a far distance. So we can say like at 10 o'clock, this person entered the black hole. And then that person goes through the black hole, and then maybe exit through the white hole, or maybe that person has died, I don't know. Then we can just measure the time, and maybe try to contact that person in a station, I guess, and ask him, hey, what time is it there? Yeah, so we don't know. Like, all of these are just based on the hypothesis. Because no one has physically entered the black holes. So we don't know how the time will move. But what we do know is the time goes very slow at the black hole because of the strong gravity. But we just don't know what's going to happen after that.
I have a question.
Yes.
What about like parallel universes? Do I think that's parallel universes?
Parallel universe? Okay, so that one requires some kind of quantum mechanics. And when we exit from the black holes, yes, we may be at another universe. So this picture shows like another galaxy here. So this one assumes that we are in the same universe, right? When we enter the black holes, like even if we exit, we are at the same universe, but it's in a different galaxy. But for the parallel universe, yes, we may end up at we may end up at another universe. But like I said before, who knows?
So all of this is just hypothetical,
Other than the black holes.
other than the black.
Other than the black holes. So that's why I said present equals the future and question mark. Because we don't know what's going to happen. But we know that the time is going very slow at the black holes. So it poses a legitimate question of time travel. But we don't know for sure whether the time travel is actually possible.
So when were the black holes for sure proved?
When was it proved? It was, so,
Was it the Schwarzschild?
yes.
So in the 20s?
And then, yeah, so it was like late 19th century.
Okay. That's really advanced for their time. That's really advanced for their time to know that. Technology is so advanced.
Yeah, so the point is the universe is like really, really huge. Like even though the technology is like developed so high these days, the universe just keeps growing and growing and the technology cannot follow.
Can a black hole like suck the Earth?
Oh yes. So basically for this black hole, which is the closest one from the Earth, when the Earth gets closer to this black hole, I think at around 8 million kilometers,
But they say that,
it
right? Like they say that it can be moved slow, like the people say that it's that far away, but it can move quickly, right? Like, can it do that? Like,
well, the black holes rotate sometimes. Now, what I'm not so sure is whether this black hole is self-rotating or is stationary. If it's stationary, then it's there.
right.
So even though the Earth is like so far away from this black hole, Earth cannot be observed because Earth is like way outside of the event horizon. But somehow, if Earth gets about this much closer to this black hole, then it will be observed. Yeah, like 8 million kilometers, which is like enormous distance still, but that's how big the event horizon is. Yeah. Yeah, so I guess the good thing is we don't have to worry about our demise because of the black holes. Yeah, there are lots of possible dangers than the black holes, like the accidents and so on. So we have to worry about those, not this. This one exists in the universe, and the scientists took the picture of that, but we don't have to worry about being sucked into these black holes. Any other questions?
Thank you.
Thank you.
Thank you.